Miss Jody here again with our second topic video on continuing on in chapter 13 on Hess's law. Now, we've been working on the bond energies and trying to figure out the thermodynamics of things. We talked about the exothermic and the exothermic reactions, if you remember, and understanding what's happening in the chemistry side of things, the energy, where's it going? Is it being released or is it being reabsorbed? And so we've done real good with calculating the bond energies and all that. Now, with this, we look at Hess's law. Now, Hess is named after the gentleman named Germain Henry Hess. He was a famous Russian chemist whose experimental work led to this particular law. And this law, since we've been focusing on enthalpy, if you remember, and just as a side note, so I don't forget to say this, I think you've got it down, but because we're going to keep trying to do the journals and glue our stuff in, all of our notes, don't forget to be taking your notes on a half sheet of paper so I can glue it right there underneath the label. But back to enthalpy. So enthalpy, we talked about enthalpy, and as an actual accurate definition, it is the energy stored in a substance. So how much energy do we have in that particular substance? And of course that relates with doing chemical reactions, because when you have chemical reactions, what's happened? You are going to be the energy is going to be moving around a little bit because the bonds have to break apart, and then they also have to, and then new things form, and some energy is released. Sometimes energy is absorbed into the other bonds, and so we have to keep track of it all. So enthalpy being how much energy is in the substance. What Hess figured out is that this is a state function. And so that's really what Hess law is based on. So what's a state function? So any quantity that depends solely on the final destination, not on the way we get to that destination. So it's basically, they give an example of traveling to an amusement park in the book. It says, okay, you're traveling to an amusement park. Somebody is going here and they take this route, the highway, and another person is going the back roads. And in the end, everybody gets to the amusement park and they have a fun day. And so when you look at that, you say, okay, what's the state function of that situation? The state function is that they all had fun. So the fun is the state function because it doesn't depend on how you got there. It's just the fact that you did get there, so you had your fun. And what's not a state function would be the number of miles it took. Like this guy, he drove a lot longer. This one going on the back roads, the amount of time it took to travel. It took him a lot longer to get there because he went the back roads. So these are not state functions because those have to do with the actual how you get there. A state function is any quantity that depends solely on just the final destination, the fact that you got there. And so they give an example in chemistry to understand this. And the example is on making water. So they say if you're going to make water, you could have two sets of H2 and bonded or reacted with two oxygens, and you'll get two water molecules. But to make another two water molecules, you could take hydrogen peroxide, 2 moles of hydrogen peroxide, and decompose it, and it would decompose into your 2 of your H2O and 1 of your O2. So it doesn't really matter which way you did it, you still got your water. And the point is that in the end, the enthalpy of this system here, H2O, 2 sets of it, is going to be the same whether you made it this way or whether you made it this way. This is going to be the same. So this is what this is focusing on, is that in the end, we don't really have to worry about like how it all formed, but that we know that the enthalpy is what it always is going to be, no matter how you form 2 sets of H2O. And so with enthalpy of a given substance, it's independent of the way that it's made. So we don't have to say, oh, if you make it this way, you get this much energy in the system. Or if you make it this way, you get this much energy. No, it's the same. It doesn't matter how you made it. It's that amount. It's locked in. It's a law. And so when we're looking at our change in enthalpy, it could be as easy as, okay, if I want to know the change in something, in my amount of energy I have, the enthalpy of each, I could take the enthalpy of each substance in my reactant side, and I could subtract out the enthalpy of each substance in my product side. But here's the problem. It's very hard to measure enthalpy of an individual substance. See, what we're normally doing, that means it's hard to measure like how much energy is in a substance. Most of the time you're measuring the change in the energy as it's going through a chemical reaction. So I have this plus this, and then in the end, how much do I have here? And so you're looking at the change more so than just, I want to know exactly how much energy is just in one substance. And so when we look at that, what we have to understand, and this would be a second page of notes, so make sure you have enough sheets when we're going along. And again, like I said before, you don't have to take down every single detail, but write it in your own words, but make sure that you have the concepts down, okay? So, so since it's kind of hard to just focus on and calculate the enthalpy of like what's in a substance, we have what's called the enthalpy of formation. And you can see this change of enthalpy with a little f there. So this is the enthalpy of a formation reaction. And so when we remember back to, I don't know which chapter it was, but we learned about decomposition reactions, formation reactions, all of those combustion reactions. A formation reaction is that forms a single substance from simpler components. So if you remember, we would do a formation reaction would be you take this, and it forms that. And so you're forming something. So if you want to figure out basically that enthalpy of formation, then you're going to run that formation reaction in a calorimeter. So that's going to be measuring the energy. So you take that reaction and you have to run it in a measurable device that can measure the amount of energy that's released, and that would be perfect in the calorimeter that we talked about last chapter. So when we are looking at that, the change in enthalpy of a chemical reaction can change depending on the conditions under which the reaction occurs. So this is a side note that we must know, that your actual change in enthalpy of that reaction can change if we have different conditions. So your conditions that this reaction is occurring in have to kind of have a set standard. So what they've done is they said, okay, most chemistry is done at room temperature, which they gave 25 degrees Celsius, and normal atmospheric pressure, which is the 1.00 atm. And they call this standard conditions. Now, they did want to clarify that this standard conditions is not exactly the same thing as a standard, what we would say the standard temp and pressure, the STP, that we normally would look at. And I can't remember where we looked at this standard. I know we did in physical science, but somewhere in chemistry we were talking about that. That might have been like when we talked about pressure and gases. But so it's not exactly the same as that, because that would be 0 degrees Celsius and then 1 atm. It's really just about standard conditions that the reaction would be in. And normally it's going to be room temperature and normal atmospheric pressure. So they created the standard enthalpies of formation and creating this little degree sign to go with it that will help us remember that that's in standard conditions that this reaction is taking place. So when we're doing this and we're looking at the formation of things and then being able to calculate that through a calorimeter, how much energy is released, it will give us an understanding of, okay, when this was formed, this much energy was released, and it was done under standard conditions, so we can get a true, accurate picture of that. Now, what's great is this is just in line with what we've already talked about. Still, we're going to have an endo and exothermic side of things. You're still going to have either it be absorbed or it be let out in the exothermic world. And then also we do have to remember that when we're talking about the change in the energy and the change in the empathy of formation here is also depending on the state of the substance. So we can't forget, like if you think of the liquid H2O, you're going to have a different amount of energy in a liquid H2O, right? Because we know, just when we learned about solid, liquid, and gases, that there's a lot of energy that's going to be needed to get that liquid H2O up to the gaseous form. So gaseous H2O is definitely going to have more energy. So you also, not only do you have to make sure that this is happening at standard conditions, but you also have to keep in mind that the number is going to change depending on whether the substance is in its liquid form, its gas form, or whatever. So those are a couple things you have to keep in mind. Now with Hess, this being a formula here to help to figure this out, we have the standard, or we have the change in empathy. There's your little degree that's explaining the standard conditions, okay, in standard conditions. And then you have this little symbol here. If you remember from algebra, this means summation, like the sum of it all. And then we have, so the sum of it all and the change in enthalpy, or the enthalpy of formation under standard conditions of the products, and then in correlation to that minus the summation of the change in enthalpy of formation of the reactants. Now, we do have to note, because our last, when we were doing bond energies, and you can remember, and I'll flip back to one here, like this one that we did, when we were doing the bond energies, we took the reactant side, this was the reactants, and we subtracted then the products. Okay, reactants, and then you subtract the products. When you look at this, you see that you have this side of it, it's your products minus your reactants. Okay, so don't get that mixed up there. So in your standard enthalpy of formation, this is another side note I meant to put in there. We do have to note when we're doing these problems that the standard enthalpy of formation, meaning the standard energy amount of the formation of something, of an element is 0. And that makes perfect sense, right? Because we're talking about the formation of these substances. Substances are going to be combinations of elements that have bonded together, compounds or elemental form, whatever, but they have a distinct formula, right? If you remember the substance world. And so they have come together and formed, we've formed them using the atoms or whatever, and they've come together, and now you have those energies holding them together. So that's what we're looking at, the bonds, you know, the single bonds, the double bonds, all those things, all that energy that's locked in there. So the standard enthalpy of formation of just an element, like just hydrogen by itself, is 0. And that makes sense because he's not bonded to anything. We're not really... we're not measuring like what's inside hydrogen, like what kind of energy we got going on in there. We know that everything's made of energy, but we're talking about the bonds and the energy in the substance. So of hydrogen by himself, that's not really, there's nothing there because there's no bonds. And then one thing they do note is that when it does come to homonuclear diatomics, and you can't barely see this because I had to squeeze it in, so I was trying to save space there. But if you remember the homonuclear diatomic sets of O2 and or two O's, the ones that have to be bonded in their sets of 2, they also have a standard enthalpy of formation as 0. Okay, now that one might be a little confusing because you got 2 sets of H's and they're bonded. So you think, well, what? That doesn't make any sense. But that is the particular rule to keep in mind with standard enthalpy of formation for the elements or those that are homonuclear diatomic. Now, with that, we have a couple of questions that I want you to do. And so this one, let me just highlight this. And then I want you to practice it on your own and try not to use the book, and unless you really need it, and see how you can figure it out. And like I said earlier in a different video, I am going to try to do a couple of these that are from the ones that would be on our quizzes and that you won't have the answers to, just to make sure that you're getting it. because I know it's nice that you have this written out in your book in case you get stuck, and I do want you to be able to use that. But then I want to also see if you can do a couple of them, and maybe that's how I'll make the with the test for our journals, have you figure one out and then snap me a picture of it. Okay, so what is the change in enthalpy? Obviously the standard conditions there of the following reaction. So we have 2NO get in its gas form, and then reacted with O2 in its gas form to create 2NO2 in its gas form. And is this exothermic or is this endothermic reaction? So you're going to be solving that using Hess's law. And I will note that there is just like on the bond energies, there's a chart for figuring out this stuff in how much is in that substance, in that formation. And it's on standard enthalpies of formation is on page 462. It's a chart. So again, stuff you don't have to memorize. This is something you would look up. But in that chart, like say for instance, the first one says what is the the first one is NO. So just NO in its gas form, and you would just look in here, and right there we have NO in its gas form. You see it right there, and its number is, or the energy is 90.3. And so you would use these to fill it out in the Hess's law equation there, and you would put it all together and then figure out whether it's exothermic and endothermic, okay? And then the second one is some gasoline companies put a small amount of liquid ethyl alcohol, which is this formula, into their gasoline. What is the change in enthalpy, standard conditions, for the complete combustion of this chemical? And so you take Hess's law, you figure it out, and don't forget, complete combustion, you've got your, you are reacting it with oxygen, and you are having products of carbon dioxide and H2O. Okay, so figure those two out, and then I'll make another video for those answers.